Hi everyone, this is our group presentation on the topic of NBA data analysis. The first part of our project is the ETL process. This table is the result of player score summary ETL. Game duration and play times are calculated and aggregated from the game time field. Other scores are averaged and summed by player, team, and year from 2010 to 2020. We use the player ETL Python file to generate clean data about the player's name, team, player ID, age, draft number, draft round, draft year, height, weight, and position from 2010 to 2020. The new data is then saved in playerinfo.csv in the ETL data folder. Injury ETL is to generate data about injury data. We filter out some useless data and create a season field from the date field. In addition, we separate nodes field into injury name and status 2 fields, which represent the type of injury and the status of getting injured, respectively. The clean data is saved in cleaninjury.csv. We use the player salary ETL to generate this data, which joins salary, player score, injury times, and physical parameters together. Some missing physical parameters are replaced by the mean value from other years of the same player. Player names are joined by ID if data is extracted from the same source, and then all special characters are removed to join on names from different data sources. In order to produce a team ability summary, we aggregate the data for each game of the team to calculate the team's average data for the 11 seasons. You can get the performance of each team in regular season from this table for further data analysis. After the ETL process, all clean data were saved in Firebase real-time database, which was a NoSQL database hosted by Google. Then our web application is connected to the database in order to read data from the database and be able to show the data. This database was a key-value pair NoSQL database. It could be used to store a large amount of unstructured or structured data from powerful processing algorithms and scale on demand to support heavy spikes in our data. In addition, the Firebase can eliminate a middle synchronization layer between the application and the backend database. The second part of our project is data analytics. MVP players and all NBA team players are essentially the same. MVP refers to the best players among all the players, and all NBA team players refers to the 3 best players in each position during the regular season. Therefore, the features to be considered are the players' data and team performance of the season. By joining the player data and team performance and putting it into a random forest classifier, we can finally get the feature importance map. We illustrate the feature importance in word cloud and histogram. The size of feature word represents its importance. Then we use a histogram plot to show the specific value of the importance. When we analyze the champion, we firstly find the feature correlation. As you can see in the heat maps, the W and the WPCD have a high correlation, so we drop the W feature. Then we use a similar method to get the feature importance. We found that WPCD is the most important feature. For further verification, we produce the histogram of the rank of WPCD and champion probability. As you can see from the results, the number 1 team in the regular season has more than 50% of chance of winning the championship, and the probability of winning the championship for the second team is about 36%. Third ranked team only has a 10% to win a championship. The teams ranked 4 to 8 have not won a championship. This also proves that WPCD is an important factor of champions.
Next, we would like to build a model that could help general team managers find the template of their new players after analyzing NBA players' similarity for the last 10 years. First, we join the datasets about player information using Spark, and then loading the information in the Jupyter Notebook for further analysis and visualization. In 2020, over 20% of players were labeled undrafted. We decided to fill in this missing value with the last valid observation, and then split our data into 2 datasets. The first one would be professional players who had NBA experience equal or more than 2 years, and others to be new players. After we normalized our data through min-max scalar function, we had 37 columns, and these multiple features would cause a long time analysis and dimensionally cursed phenomenon. Therefore, we would like to compress our features using the PCA function. We'll scikit-learn, the decomposition library in Python. When component n equals 8, 94% of data variants were kept, which was pretty good. We could then easily find the template of this new new player by computing the distance between different players and figure out the professional player close to him. For example, here, we randomly pick a new player, Orlando Johnson, from the list. This is all the new player name, and we randomly pick this. And then the Jerry Stackhouse is one of the professional players who has the most similarity in NBA performance with Orlando. For visualization, we decided to compress our feature to be two principal components, which could be more intuitive to show our results. And 76% variance were kept, which is acceptable in general. Here we use the same Orlando Johnson here. For this time, in the same position, Kirk Hinrich became the closed player. Look at this image. Since we have over 5,000 professional players, it is impossible to clearly show all the names on this plot. So we update a new professional player list, which contains only the top 100 basketball players. And it can clearly show the distance between different points and mark the new players we put in. Here is our results. This is Orlando Johnson. Different colors means different positions. So Joe Henrys is the professional players who has the most similarity performance with Orlando. And if you want to show this result by yourself, you can simply run this Python. There it is. This is a Python file, and this is the results, which is same as what I just showing. And the output file contains all the plots. And that is all for this part, I think.
As an NBA team manager, the team's competitiveness always comes first. The NBA team managers need to be concerned about players' competitiveness and influence on the games. For the players, even though they have very high competitiveness, as their age increases or they get injured more and more often, their influence on the games could decrease. In this way, team managers need to be concerned about the influence of age and injury to the players. For most injury player Python file and most injury team Python file, we plot bar graphs about the top players who mostly get injured and top teams who mostly suffer injury events. From the plots, we can see the relationship between injury and teams. In the file injuries types.py, we plot graphs about the frequency of injury type in each position. From these graphs, we can see the relationship between injury and position. The larger the word size is in the plot, the more times the word occurs. Before training models, graphs about the correlation of all features in the dataset are made in order to perform feature selection. After checking the correlation plot, the selected features include the last season, stat, age, height, weight, how many injury players got, status after injury, and player position. I will be showing how the code runs for this part at the back end while I'm talking. We tried to train models to predict player stat in the next season based on age, height, weight, last season age, the number of times the injury events happened, and the status after injury event. The data we used to train the model came from three parts: claimed injury data, player info data, and player stat data. We merged them together and then separated the dataset into training and validation part. We used the training part to train the model and validation part to test the model. The cross-validation module in the Spark machine learning library is used to find the best model. We used R-squared as a score to determine whether the model is good. Based on our fitted models, we also implemented the feature to launch a demo, where you can enter the input feature values, height, number of injuries, average points, choose a player position, and injury status. Click Submit, it will pop up the results immediately. The models that predict next season average point, assist, steals, and blocks are linear models. During training, we compute the residual plot about the prediction and features, true versus predict, and scatter plot about the actual value and features. After checking the residual plot, we decided to transform the feature of the number of injuries using a log, since the residual plot about the residual and the number of injuries is screwed. The R-squared of predicting next season average point, average assist, average steal, and average rebound are from 0.69 to 0.82. For the models that predict next season's offensive rebound and defensive rebound, we used a random forest model and also plot the feature importance plot to show all important features. The R-squared value is in the range from 0.63 to 0.75. This part is about NBA salary. Salary is something people are always curious about. Analysis and predictions of salary could not only help keeping the salary cap, but also engage players to set up clear goals on better achievements to get a higher salary. We would like to make a model to predict the player's salary depending on players' performance and their physical conditions. This model will also help NBA general managers to simulate their team ahead of time based on the funds available. The box plots here provides a general idea of NBA salary distribution for each year. 2013 seems to have the highest mean salary, and 2017 has the widest range. The player's average salary is around $3 million. For interest, in the 2017 season, Stephen Curry got the highest NBA salary at around $34.68 million. This density plot provides a general idea of overall salary rates. Not very surprising since we have seen the box plots. It's red screwed by some famous player with extremely high salaries. The heat map shows how much correlation there is between each pair of variables. The closer it is to 1 or minus 1, the higher correlations there are. In this case, the closer blocks are to white color indicates higher correlation. There are some light blocks for a few pairs of scores. Might need to consider feature selection later. Then we would like to predict salaries using the game durations, place, physical parameters, injuries, and scores. The model is fitted using a pipeline. Features are normalized since there are big variations among some features. We are using regressors since our prediction of salary is a continuous number. Generalized linear regression, GPT regressor, trees, and random forest with testing out different parameters are computed, and validation R-squared is around 0.6. Learning from the model, average field goals made, average points, and age resulted to be the top 3 most important features, which relates to salary the most. Our fitted value are shown in the plot. If red dots are close to the blue line, then it's a good fit. For user convenience, this is the same functionality of what we have demoed on the previous tab. Values can be entered to get a prediction of salary. These are what we have done for this project. We would love to further develop on this topic sometime in the future. Hope you find this analysis useful for NBA team managers and maybe other audiences. Thanks for watching.